propose a novel, physics-inspired 3D feature fusion framework, named FHGS, that freezes pre-trained features from 2D vision models and robustly distills them into 3D scenes. Our method not only significantly improves the quality of feature fusion and the accuracy of geometric reconstruction, but also boosts training efficiency by several orders of magnitude. In recent years, 3D Gaussian splatting 3D has begun to reshape 3D scene representation through its combination of real-time rendering and high-fidelity reconstruction. In parallel, 2D vision foundation models, such as SAM, CLIP, and Dino, have made substantial progress in image-level, semantic understanding. For robotic systems, including vision language, navigation, VLN, and task planning, it is therefore crucial to have a 3D scene representation that not only captures accurate geometry, but also carries rich semantic information. This naturally leads to the question, can we inject the strong semantic understanding ability of 2D foundation models into the finely detailed 3D spaces constructed by 3DGs so as to obtain a 3D world that can both see and semantically interpret its environment? This is precisely the core problem addressed by feature field research, and it is directly relevant to downstream tasks such as robot navigation, 3D scene editing, and segmentation. To address these issues, we propose the FHGS framework, whose core idea is decoupling and guidance. First, we introduce a universal fusion architecture that unifies semantic features from 2D foundation models into a 3D Gaussian representation. The framework starts from multi-view images. SFM recovers camera poses and an initial 3D point cloud. A pre-trained 2D model with a hash encoder extracts per pixel features, and Gaussian primitives are initialized on the SFM points, optimized through a differentiable rasterization pipeline with adaptive density control, thereby jointly learning a 3D feature field and RGB appearance. Second, we design a non-differentiable feature driving scheme that leverages feature losses to update only the geometry and opacity of Gaussian, while keeping the GS features themselves frozen. Third, we introduce a physics-inspired dual-drive optimization that uses two complementary forces to enforce global alignment and local coherence in the learned feature field. In FHGS, we no longer treat features as learnable, color-like quantities, but instead, regard them as fixed, non-differentiable, semantic labels. The high-dimensional descriptors extracted from 2D foundation models are frozen in 3D and never modified during optimization, thereby preserving their original semantic structure and fundamentally avoiding feature distortion. The original 3DG's framework performs ellipsoid 2-pixel splatting, whereas NDFD can be interpreted as pixels emitting semantic rays that drive the ellipsoids. This pixel-to-ellipsoid radiation pattern naturally parallels electric field lines acting on charged particles. Within FHGS, we thus decompose optimization into two complementary paths: a differentiable rasterization framework, DRF, green path in the figure, that uses a standard differentiable renderer, and an RGB loss, to update only Gaussian colors and refine photorealistic appearance, and a non-differentiable feature-driving branch NDFD, orange path that applies losses directly in feature space, updating only Gaussian geometry and opacity, while bypassing the renderer and using high-level semantics to shape scene structure. This decoupling makes geometric optimization more stable and semantically consistent, while still yielding highly realistic rendered images. The most intriguing aspect of our method is that we design the optimization mechanism by borrowing the physical model of charged particles moving in an electric field. We treat the ground truth features from 2D images as a strong external field, and each Gaussian primitive in the scene as a charge carrying its own feature. The optimization objective is to drive these charges under the action of this field toward low potential positions, that is, locations whose features are most similar to the ground truth. To obtain a cleaner feature field, we further introduce an interaction force between charges that follows a like attracts, a like repels principle. Gaussians with similar semantics are encouraged to cluster in space, while those with large semantic discrepancies are pushed apart, which suppresses noise and sharpens semantic boundaries. Under this dual drive mechanism, we keep all features frozen and never update them by backpropagation. Instead, we indirectly shape the semantic field by optimizing geometric parameters of the Gaussian such as position, shape, and opacity, thereby achieving consistent semantic representations across multiple views and elegantly resolving the fundamental conflict described above. On the DTU24 dataset, our ablation study shows that every component of the proposed dual drive mechanism is essential. In terms of feature reconstruction, FHGS recovers clear, accurate features that are highly consistent with the ground truth. When the consistency loss is removed, convergence becomes faster but semantic noise increases significantly, and geometric details degrade, while the 2DGS baseline produces globally blurred and distorted features. In the corresponding 3D geometry, the full doulas configuration yields compact structures, with sharp boundaries, that remain stable and consistent under novel views, confirming the effectiveness of our dual-drive strategy for both feature fusion and geometric reconstruction. We conduct systematic experiments on multiple public datasets, including the indoor DTU and the outdoor MIPNERV360, and FHGS shows clear advantages in 3 aspects. First, it achieves higher feature fusion quality. The reconstructed features are cleaner, semantic boundaries are sharper, and background noise is significantly reduced compared with Feature 3D. Second, it delivers better geometric reconstruction and denoising. Semantic cues directly guide geometric optimization, leading to smoother and more complete surfaces, while effectively suppressing speckles and floating artifacts. Finally, training efficiency is greatly improved, thanks to NDFD and the physics-inspired design. The training time of FHGS is reduced from the 24-hour scale of Feature 3DGS to about 5 minutes, even faster than our 2DGS baseline, making practical and near real-time applications feasible. By jointly examining the 3 tables, we can clearly see the overall behavior of FHGS on indoor, outdoor, and 3D reconstruction tasks. First, from Table 1, FHGS achieves indoor PSNR that is comparable to Feature 3DGS, while attaining the best FA and FL1 scores. Moreover, each scene can be trained within only a few minutes, yielding a speedup of more than 1 order of magnitude over Feature 3DGS, and even slightly outperforming 2D. Second, in Table 2, FHGS attains the lowest Phi and FL1 across all outdoor scenes, indicating the strongest semantic consistency. At the same time, its training time is far shorter than that of Feature 3D, with only a slight drop in PSNR, in shadowed or fragmented, low semantic regions, which is a reasonable trade-off between semantic quality and rendering metrics. Finally, Table 3 reports results on the DTU dataset, where FHGS achieves the lowest chamfer distance, and thus the most accurate geometry, while maintaining near-optimal PSNR, using fewer Gaussians, and reducing per-scene training time from more than 24 hours to under 5 minutes. In terms of PSNR on rendered images, FHGS clearly outperforms 2DGS on indoor datasets, but shows a slight drop in outdoor scenes. This decrease mainly arises from shadows, the regions highlighted in yellow in the figure, fragmented soil patterns, and other fine-grained textures with low semantic content. Although these regions have little impact on semantic perception, they degrade pixel-level metrics such as PS, leading to a gain, indoors, trade-off, outdoors phenomenon.